Neural networks are found a lot in modern day technology. They are, for instance, used in your favorite voice-controlled home assistant, used in producing and driving cars, or to diagnose diseases in medical applications. But what exactly is a neural net? And how is it able to remember information for a given task? That's exactly what we are going to find out today. I will start from the very basics and hope to build up your understanding of the matter from the ground up. This video is only the first one of a couple I have planned around this topic. So if you don't want to miss the next one, hit subscribe now. I also have outlets on Facebook and Instagram for some behind the scenes info. And if you like to discuss this topic with other like-minded people and me, we have a Discord server now. All the links are in the description below. What you will learn. First, we will talk about a neural net from a bird's eye perspective. After that, we will deep dive into the math of one neuron to try to understand how it makes a decision and is able to retain information for a given task. Beware, there will be some math involved, but if you are confident adding and multiplying numbers, you are good to go. Moving on, it is time to understand the limitations of one neuron and how a net of neurons is able to overcome these. While we are doing all of this, we will also put it into Python code. We really got a lot to do today. If you're already familiar with this matter, please don't hesitate to use the timestamps in the description below to skip to another part of this video. And now, without further ado, let's get started. What is a neural network? The idea of a neural net is based on biology. In your brain and throughout your nervous system, there are little cells called neurons. Most neurons have a cell body, dendrites, and an axon. The dendrites of one neuron receive information from other neurons. This information is combined in the cell body, leading to a potential. Each neuron has an activation threshold. If the potential reaches the activation threshold, pulses are generated by this neuron and sent out via the axon to other connected neurons. The connections between neurons can be stronger and weaker, which means some incoming information from other neurons have a bigger influence on the activation of a neuron. This is how neurons form nets, store information, and make decisions. Conceptually, a common net looks like this. We have an input layer in which information from the outside system arrives. This information is then processed by one or multiple layers of neurons and arrives at the output layer where the rest of the system can receive the information from the neural net. As in biology, some connections are stronger than others. We then talk about some inputs having bigger weights, here shown with thicker lines. Not all neurons from one layer need to be connected to all the other neurons of the next layer. In fact, the connections of the different neurons are pretty arbitrary, and there are a lot of different structures of neural nets out there. There are even some nets that connect back from one layer to its previous layers. In this video whatsoever, we will just examine the workings of a so-called feed-forward network, in which one layer feeds its information only to the following layers. But the math stays the same, no matter what your net is structured like. On that note, let's move on and examine the math of one neuron in a neural net. A neuron, or you might find the name perceptron here and there as well, consists of 5 parts. A couple of inputs with associated weights, a bias, a sum, and an activation function. Mathematically, it looks like this. The weighted sum of the inputs plus the bias is put through an activation function, and what comes out at the other end is the output of the neuron. In order to explain all the different parts and why and how they work together, let's use an example. Like a lot of others, I like a good whiskey from time to time, in particular Scotch. But there are a lot of different whiskies on the market, and I would love to know if I like a whiskey before buying it or not. This problem is called a classification problem, and we can use a neural network to answer this question for me. Actually, just one neuron is enough in this simplified example to make this decision. Specifically, we want to have a neuron that puts the whiskies into 2 categories. Whiskies I probably like and whiskies I shouldn't try in the first place. In order to build our neural network, we need some data. So I went out of my way and tried some whiskeys and jotted down if I liked them or not. Now we need some properties we can use to distinguish these whiskeys. These will be the input to our neuron. So basically we need to decide now how we can encode each whiskey into numbers to feed it into the inputs of our neuron. And this is not as easy as it may seem. There are countless ways to create a numerical representation of a whiskey, like measuring its color and handing it over as a floating point value using the age of the whiskey or the geo-coordinates of its brewery. If you don't provide your net with the right inputs, it will come to very funky conclusions. For instance, if I would hand in the name of the whiskey and its brightness, the output later might be that I like whiskeys starting with a G and having a brightness of less than 40% or something like that. That this would lead to a crappy output seems obvious for this example, but in real-world applications it is often not that easy. All of this is enough material for a video on its own, and I will not cover it further in this video, but I wanted to mention it here because otherwise you won't have a lot of fun with your neural nets. For our example, I went with 2 input parameters per whiskey. How full is the whiskey in taste? I call this richness. And how smoky is the whiskey? Smokiness. Using these, I can put all the whiskeys I have tried on a 2-dimensional plane like this. You might see now that we could draw a line between the whiskeys I like and the ones I don't like to separate them into 2 groups like this. And this is basically what one neuron does. Let me show you. Our neuron has 2 inputs, R and S, weights for each of these, a bias, a sum of these inputs, and an activation function. Looking at the sum inside of the activation function F, you might recognize this as the standard form of a line in a 2-dimensional space. If not, here's a little recap for you. Most of us know that you can describe a straight line in 2D space using the slope-intercept equation, y equals mx plus b, in which m is the slope and b is the y-axis intercept. Our 2D plane doesn't use x and y as axes, but richness r and smokiness s. So s equals mr plus b. Our drawn line intercepts the smokiness axis at around 0.25 and its slope is approximately 0.45 per richness. Putting these values in, we get s equals 0.45r plus 0.25. But this doesn't look like our sum inside the activation function. That's because we have to go from slope-intercept to standard form. First, we subtract 0.45r and after that we subtract 0.25. Giving us s minus 0.45r minus 0.25. We now have the same straight line described in standard form. If we map the first half of this equation to our sum inside of our neuron, we can see that w1 has to be equal to 1 and that w2 is equal to minus 0.45. The bias, which takes the role of our smokiness axis intercept, is minus 0.25. If I were to put the richness and smokiness of a whiskey I like, Glenmorangie for example, into this equation, the result is negative. But if I put the values for Talisker, that I'm not really a fan of, into this equation, the result is positive. And this is actually true for all the whiskies. So this function categorized them into 2 categories, giving all the whiskies above the line a positive value and all the whiskies below the line a negative one. The fact that the values for whiskies I like are negative numbers and the ones I dislike have positive values doesn't really matter. The only thing that matters is that the sign of the values in these 2 categories differ. And you might have realized by now the bias of a neuron is the axis intercept of its straight line. Without it, we couldn't move away from the origin of the value space, which would really limit the ability of our neurons to separate the value space into categories. We have now calculated the activation value of our neuron for each of the whiskies. The activation value of a neuron is the weighted sum of its inputs and the bias. And this is what's handed over to the activation function. The activation function is what models the activation threshold in a biological neuron. It basically tells the neuron when to and how to output information to the rest of the net or the underlying system. But there's more. The activation function shapes the output of the neuron to be inside a certain range. Basically, with the choice of our activation function, we decide how we want this neuron to pass on the decision it has made to the next neuron in line. This is important because we sometimes don't want to pass on how strong the decision is a neuron has made, but only the decision itself. So there are a lot of different activation functions used in neural networks. Here are some examples for you to look at. This is just a subset of commonly used activation functions. There are a lot more. The choice of your activation functions within your neural net depends on multiple factors. It depends on the problem you are trying to solve, the structure of your net, and also the training algorithm you want to use. But I'm getting ahead of myself. In our simple example, we only have one neuron, and I will use the step function here. The step function returns a 1 for all positive inputs and a 0 for all the rest. Now we can put everything together in our neuron, which results in the finished equation like this. As you can see, the two incoming inputs have the weights 1 and minus 0.45, and the bias is minus 0.25. All of this now goes through the step function, so we will get a 0 for all the whiskeys I like and a 1 for all the whiskeys I better not try. Let's put the Glenmorangie and the Talisker through this neuron now and see if we get the expected output values. Perfect! By now you should hopefully understand how one neuron makes its decisions and how the math behind it actually works. Let me know in the comments below what your favorite whiskey is, or if you have any questions up until now whatsoever. One word on the number of input parameters. You might think that this works only for 2 input parameters, but I can assure you all of the math above applies for 3 or more input parameters as well. Instead of separating 2 classes of data by a straight line, you can separate them using a plane in a 3-dimensional input value space, or with higher dimensionality, it works using a hyperplane. But all of that is rather hard to draw, so I go with the easy path of just 2 dimensions in this video. Before we move on to actually build a net of neurons, let's put this neuron into some Python code first. As always, I start with defining some data types. Yes, there is a type system in Python. If you want to know more about why you would use a type system and how to use it, I have a couple of videos about this topic on my channel as well. The first type I define is a vector. A vector is nothing more than a list of floating point values. We will program a general implementation of a neuron here, and we will use vectors to hand in the input values and the weights to our neuron. Next, there is a type for an activation function. It is defined as being a callable with one floating point input parameter and a return value of type float. That's all types we need right now. Let's move on to implement the neuron. The neuron is implemented as a function. It takes a vector of inputs and a vector of weights. The last parameter defines the activation function we want to use with our neuron. Before I go over the lines of code, here is a short reminder of what the zip function in Python does. Python's zip function takes an indefinite number of lists as input and joins all the values together in one list. Each item in the resulting list is a tuple of the values in the incoming lists at the same index. The resulting list has the same length as the shortest incoming list. Elements from longer lists are discarded. Alright, back to our neuron. The neuron function is implemented with a couple of nested function calls. Starting from the inside, the first thing we need to do is zip the list of inputs and the list of weights. But wait, there's also a 1 attached at the beginning of the inputs. Why? This is a little trick that is used to store the bias of a neuron as the first element of the weights. So what we basically do is to think of the bias as an extra input to the neuron with a weight of 1. After we have zipped the 2 lists, we can now iterate over each tuple inside of the zipped list and multiply its values. This results in a new list in which we store the multiplication of the bias with 1, the multiplication of the first input value with the first input weight, the second input with the second weight, and so on. In order to get our sum, we sum up all the values in the list of the multiplication results. This results in our activation value of the neuron, which we then hand over to the activation function. That's it. We can now return the output of our neuron. Next, we need our activation function. We settled for the step function, and this is how we implement it. It simply returns 1 if the incoming value x is greater than 0. Otherwise, we return 0. And now we can put everything together. First, we define our weights. The first value in this list is the bias of our neuron, followed by the weight for the incoming smokiness, and followed by the weight for the incoming richness of a whiskey. Now we define some input values for the Glamorgangie and the Talisker. If we call our neuron function now with the weights and the inputs for the two whiskies, we should get a 0 for the Glamorgangie and a 1 for the Talisker. There you go. So why and when do we need a network of neurons? What we have done until now hardly counts as a neural network because there was no network of neurons. And you might ask yourself, why would we even need more neurons? The whiskey prediction works quite well, doesn't it? Let's talk about the limitations of one neuron and how a neural net can overcome them. I have prepared another example to give you a feeling for why a neural network actually exists in the first place. If you are watching this channel, you are most likely a little familiar with programming, and you most certainly have encountered the OR function. The OR function takes in two binary values of 0 and 1 and outputs a 1 if one of the values is a 1. If we put this data on a 2D plane again, we can draw a line and calculate our weights and bias for our neuron. If we now inject the values for A and B into our neuron, we get the expected values back. The same works for AND and not AND. Let's have a look at exclusive OR now. The exclusive OR function only returns 1 if both input values are not the same. After putting this on a 2D plane, we have a problem. There is no way of separating the red from the green dots by a straight line. This means a single neuron is not capable of modeling this function. Only if our dataset can be separated by a straight line, we can use a single neuron. But we can use a network of neurons to model the XOR function. Specifically, we can combine an AND neuron, an OR neuron together with a not AND neuron to get the desired output. In electronics, an XOR circuit can be constructed by combining a NAND, OR and AND gate. Likewise, we can put our three neurons together to create a neural net that is able to calculate the XOR function. We can build a two-layer neural net using our NAND and OR neuron as the first layer, feeding their output into the AND neuron that will generate the output for the entire net. Let's try it out for some values. For the input 0, 0, the OR neuron returns a 0, which leads the AND neuron to output a 0 for the entire net. For the input 1, 1, on the other hand, the NAND neuron returns 0, and for that the output of the net equals 0 as well. For the inputs 0, 1 and 1, 0, both OR and NAND neuron return a 1, which results in a 1 for the result of the net after the AND neuron. This is how a neural net can learn more than its single neurons and how it is able to model very complex functions. You also saw here how layers of neurons output their decisions to the next layer. Now it's time to put all of this together in Python. Starting with our neuron and step function from the whiskey neuron, the first thing we need to do is to define the weights for our NAND, OR and AND neurons. After that, we can define our XOR net. This function only takes a vector of inputs. Inside we have a nested function call calling first the NAND and OR neuron with the given inputs and using the returned values as input for our AND neuron. The result of the last neuron call is the result of the entire XOR net, which is returned. In order to test our net, I define a list of inputs I want to hand over to the net. I then iterate over the inputs and call the net with each of them. In order to see something, I print the input values followed by the results of the neural net call. Perfect! Our neural net calculated the XOR function correctly. Congratulations! You just programmed your first neural net in Python. But up until now we have just put together some neurons manually and we found the values for our weights and biases using basic math. But how can a neural net learn from arbitrary data. This is called training, and it will be the topic of another video in this series. We will also look at how neural nets can make decisions on other types of data. How we can, for instance, hand in a picture of a handwritten number and get the numerical value of this number itself. All of this and more will come up very soon. So if you don't want to miss it, please consider subscribing to the channel and hit the like button to help the YouTube algorithm learn that you like this kind of video. I hope that you have a basic understanding of the inner workings of a neural net by now. If you have any questions whatsoever, please don't hesitate to comment below or join the Discord server to directly interact with other coders and me. Until we progress on our journey deeper down the rabbit hole of neural net machine learning, here are some videos for you to enjoy. I see you next time. Have a lot of fun, coders!